Okay, here we go. All right, so this is the part that we're making for the grounds department. So this is a bracket for a large snowplow. Obviously, it's broken. So what we want to do is we're going to make a copy. The first thing first is let's look at the original and see what we got here. So of note, let's kind of look at the welds on here. You know, I mean, what do you see? Take a look at the welds on here. Let's take a look. There's another one right there. So everything we've learned about welds and welding, weld joints, what do you see? Anything of note that you notice about these?
I mean, this one's broken.
I think rusty.
Yeah, this one, if you notice, see how these are only welded on one side? These ones, and look what happened, they kind of like butterflied out like this. So because these brackets are only welded on one side, any force whatsoever has pushed them open like this. So what I'd like to do is, well, I don't want this to happen. It's kind of poor practice. It looks terrible. We know better than that. So the challenge here is it's got to be welded here, but it's also going to be welded on the inside. So you have a very narrow space. In fact, this is only 3/4 of an inch. So you need to figure out how to get in there. Now, that can go a lot to say selection of process. What kind of welding process are you going to use? We have parameters. We have a very narrow space in here. How can we get in there? Other things of note on here, if you look at the welds, some of them, the ends over here, what do you notice about that?
Oh, okay, yeah.
Yeah, there's a big hole there. So in a lot of these, whenever you've got things like this, brackets or whatever, the weld symbol for something like this would be like, you know, I point this in a weld all around, in which case you would continuously weld the entire weld without stopping. As a rule, whenever you've got anything like this, structural or thing like this, you never want to leave any open ends like that. What happens is snow, moisture, salt gets inside of here, and then eventually over time it's going to weaken this weld joint. It may look okay from this side, but you see how easily this thing butterflied right here? If the salt is busy eating that away from underneath, it goes a long way towards making it weak when forces are applied. So always the standard practice, never leave these ends unwelded. That's just, it's very poor practice. It really is. This is like, it's bad, very bad, the worst craftsmanship. So don't do that. We always want to make sure everything's welded, completely sealed so moisture can't get in there. Another one is, some of these brackets over here, if you notice this, here's one too, look at that.
It's crooked.
And what do you notice right there?
Oh, it's not flush.
And what's it missing?
Oh, the weld.
It's missing a weld. So in this case, what they did was it's almost a weird stagger here. They said, all right, well, I'll weld one side here, but then one's in, but now leave them alone. But what good is that? Because when you think about it, if I've got my piece like this, and I have a weld here and a weld here, and that's it, it kind of means this thing can kind of, it's not structurally very strong. It's weak in two directions. It almost can do, if you apply force on it, it's going to do this. It's going to move on it. It's weak, so it's almost like pushing, and it wants to do this. So, what's so hard about using a few more seconds and actually putting a weld there? Plus, you notice it's also rusty, so water's right inside of it.
Yeah.
So, just use common sense, all right? Where you want to make sure all these are welded out. So when we do this, we want to make sure that all of the weld.
The company that makes the plow?
Yes.
So that's like, yeah.
This was made by the manufacturer. Now, there could be several reasons for this. Now, the one I'm making here is actually beefed up. This is kind of stronger, the metal's better, it's a little bit better made. One thing to remember about the way things are made is that you may see this very often where you're like, wow, why is it so craptastic? What happened here? Yeah, I like that word. Because you have to remember, sometimes things are made to a price point. If they make them perfect, it may cost way too much money. They might say, you know what, we can only budget, I don't know, $500 for this part, but the way you're welding it, now you've turned it into like a $2,000 part. It takes too much
I
time.
think we talked about also last week about
Same thing with the truck bed.
Yeah, where like, you make it too good, then
Yeah, it'll never break, exactly. If you make it so good, it may never wear out. Now, being as I'm making this in-house for our own department, I'm putting, I put a lot of time into redesigning this thing and making these parts much better than the originals. Retail for this is $2,500, which is kind of like, what? Why is it so expensive? Well, time and money, and when you think about it, they may charge like $70 to $100 per person per hour, okay, to fabricate this, and then included in like above the cost of the material itself. So that's where a lot of times, why are a lot of this fabrication so expensive? Because of the per people hours. Why it's important is when it comes time for you, if somebody says to you like, hey, can you make this for me? You gotta remember, you need to budget your hours accordingly. Pay yourself first, that's the rule. How much are you worth? Okay? Now, I budget my time anywhere between $50 to $100 per hour, depending who I'm working for. It's a friend, $50. Somebody I don't know, it could be $100. Though sometimes I'll do stuff for free. Because somebody I know is really hard up and I'm donating my time, I do stuff for free all the time too. That's fine. But if it's a money job, remember to pay yourself, okay? As you get better in your workmanship, you're a student right now. You may say, oh, $25, an hour or something. Then maybe a few years later, you're like, you know what, I'm worth 35 now. I'm worth 40. So as you gain in skill, estimate what you're worth, This is good when you go to a job and somebody says, well, I'll pay you $50 an hour. And you're like, wait a minute, is that, am I worth $50 an hour? Am I worth more? So that's actually that's a very complicated conversation for people who make things. How much is my time worth? And it's very common for us who make stuff where you realize at the start, you're like, crap, why am I selling stuff so cheap? It takes me 8 hours to make this thing, and I'm selling it for like $100. You do the math, dude, do the math. How much money per hour am I making? So you want to make sure that whatever you get charging people, can you make a living off this? How much money do you need to pay your bills, to do what you need to do? It's just, you got to be real about that and be very careful. It's infamous in the crafts industry for people to sell themselves short. They work their asses off making things they love to sell to people, and then they realize later, wow, I'm not making any money. I'm blowing tons of money, buying materials, working, and I'm selling stuff on the cheap, where realistically, this object should be a lot more money. This is why stuff is expensive. Handmade things are expensive. When I was carving wooden swords some years ago, one of the businesses I did, they were anywhere between, they're training weapons for martial arts. And I used to make them by hand because the sword, there are not a lot of good ones out there. I custom made them for people. I would charge usually between $350 to $500 a piece. Why so much? Because some cases it was, it was a better part of the day to do, with very scary tools and required a lot of precision. In some cases, that's things that cost $1,000 because, well, how much is my time worth? I'm working for several days on this project. How much is your workday worth? If we're working out there, we expect to get at least $1,000 a week, right? Come on. Otherwise, we're just not working to our full potential. So this is something you really have to think about. Even though if you're young and you're starting, it's a very mature conversation you got to think about. What's your time worth,
So if it's 60 pounds, how much would that be?
What do you mean?
How long would that take you to get the object is 60 pounds?
The object itself?
Yeah.
You have to think about, I don't know what it looks like or anything. It's not by weight. I know the book has a weird thing, but really you have to estimate the job. And that comes with experience. When you look at something like this, it's like, all right, like a client came and said, well, how long does it take to do this? And I was like, it's going to be a while. It's a complicated project. So here they are in a rush. But realistically, you have to think, well, what can I do? How many processes were involved in this? A lot. So what are we going to do? So with this kind of project, this is what they brought in first. So here it is. All right, here they are. And here are the steps I did in order to figure out how to do this project. So step one, what have I got? So what is this made of? What kind of metal is it? So I got mild steel, size. So the next thing is measuring this. Now remember, metal all comes in standard shapes. So none of this is exotic. Okay, a big part of the work process in fabrication is knowing what shapes metal comes in. Okay, what will I have here? So this is called an angle, and because it's an angle, and angles can have either equal length or unequal length legs, and this is an unequal length leg angle. They come in standard sizes. So in this case, right here, this one is a 3.5 by 2.5 angle. Now, sizes come, it's almost like shoes. They come in whole and half sizes. So if you need an angle that's like, well, I need one that's 2 7/8. They don't come in that size. So your next option is, well, I got to buy a bigger one, and I got to cut it down. Yeah, so this can complicate stuff. If you need a weird size, then you're like, well, I'm going to cut it down. To cut it down, what tools do I have to do that? Do I have access to a large, maybe if I have a really big bandsaw, I can feed it in, plasma cutter, an oxyacetylene torch, or worst comes to worst, you could actually shave it down with an angle grinder. It would be very, very difficult, extremely unpleasant, very unpleasant, but you can do it. So all these shapes come in, like this one is 3/8 of an inch. So again, you get standard sizes, 1/16 of an inch, 1/8 inch, 1/4 inch, 3/8 of an inch, 1/2 an inch, maybe 5/16. So if you have an oddball thickness, then you can run into some weird problems. This comes into play if you're doing a job, and this happened to me. The client is actually overseas, and everything they do is in metric. Now the fun thing is,
change it.
yeah, and the thing is, the conversions are not the same. So in Europe, their metal may come in like, all right, 4mm, 6mm, 8mm, 10mm. There's no exact conversion between fractional and metric. So you may come up with knowledge, you're like, wait, I need a 6mm thick piece for this job, but the closest thing is 1/4 inch is actually a little smaller. So this affects the whole strength issue. You don't have the required strength. So you have to do a lot of thinking, what can we go bigger? Can I use a thicker piece of metal for the same job? Is it allowed? So these are all the things that come into play in fabrication where measuring is really key here. What kind of thickness metal do I have? What does the Mid-City Steel we order from? Do they carry it? Some cases I've asked them, say, oh, we don't carry that size tube. Okay, but we have this. What kind of substitute? So this
So
one,
this one is obviously a lot bigger.
it is, yes.
So-
it is a lot bigger, yeah.
So, but you're saying, for you though, for this project, that's
Mhm.
not a problem?
No, that's not, because we looked at this carefully, and the reason why we went bigger is we wanted better strength.
Right.
And what we noticed is this, well, we got holes on here. So if you got holes, what does that tell you?
The frame is, what is it, what is slots?
Well, these aren't going to be slot welds. These are holes, which means it does what? It attaches to something else.
Yeah.
It attaches to something else. So the bolt holes mean it attaches to something else. So what we did is we looked carefully at the other parts and said, all right, well, we can actually make it thicker, and that's not going to impact how it bolts up to something else. So in this case, if there's nothing in the way, there's nothing impacting it, so let's go thicker.
So you didn't add these holes, these already were in them?
Well, I'm copying these. These were drilled, so we
No,
would
okay.
drill them in.
Yeah, that's right.
We're copying the existing bolt
Right.
pattern from here to there.
Okay.
So we copied it. They didn't come like this. So
See,
we have
that's
to put
why
the whole-
when you asked me that question, that's why.
Oh, okay, I'm sorry.
Yeah.
So is this a little shorter this
It's,
way then? Like,
oh no, it's
because
exactly the
it's
same.
exactly the same?
Yeah, this will actually go here.
Oh,
Yeah,
okay,
sorry,
that's
yeah.
right.
So we're copying the bolt pattern from here to here. So what we had to do here is make sure everything lines up very carefully. So students last year, they measured this up very carefully and copied the hole pattern from here to here exactly. That took a while. And that way this will bolt up the existing pieces on the truck, hopefully. This is kind of nice. So here are these ears right here, like that. On the back, the new ears, this was kind of cool. So how am I going to keep these in the right orientation and keep them from moving on me? So what I did was I found a piece of material, aluminum, that's the same thickness as this, the space. It's clamped in place. And I went to the lathe and turned a piece of aluminum to fit just inside the hole. So now the whole assembly is, yeah, it's all clamped together. And I can put it in place just like this. And added bonus is I take my square, oops, I put it here, I can use this to make sure it's dead perpendicular when it's tacked up. So one person can hold it like this, and then your partner does the tacking. Yeah.
And then once it's tacked, you can undo it.
Then I pull it off and I check. So what we want to do here is, how are we going to tack it together? So what we want to do here is this, okay? Notice AA and BB. So we want to keep these two sets together. So what we want to do is this. On the table here, what we want to do is we want to line up each part so that they're like the right line, like see they're lined up right here? So what you want to do is, taking a square, you can line up against one of the brackets here, line this bracket up right with it. I recommend a hammer. You can really mess up your hand with doing this. You want to get this one aligned perfectly with this one, okay? Take another square, which we have laying around here. Check this for perpendicularity right here, to make sure it's straight up and down. Then you tack it, okay? So what you want to do is tack it in, when you tack, yeah, 3 places, that way it doesn't move. So I recommend is tack it once, check it, make sure it's straight. If you're absolutely sure, you're satisfied it's straight, 2, then 3, okay? So we want to do that with all of these parts. So copy exactly what you see here, okay? If this has a reinforcement plate here, don't put one in right there. Just like that. All the way around, okay? And there's parts for everything on both of these things. So what we want to do is we want to tackle this, we want to tack it together. Then we want to go back, check the whole thing, make sure it's perfect. Okay? And the procedure would be this. Once it's tacked up, now the tacks have to be good because we want to have Connor's going to pick them up, check them against the snowplow. He's bolted the entire assembly up onto the snowplow.
Well, it's tacked.
While it's tacked, which means tacks have to hold. They'll be strong enough to hold, yet if something's wrong, they must be able to be removed. Okay? So we want to make sure that that's possible. So they can't be too big. You have to be able to cut them to remove it if something's like, oh, this thing needs to be bigger or whatever. They'll check it, and once you have approval, then you weld it out. So this is a universal thing you should always do, okay? Tack it up completely, double check all your measurements, everything, over again against the print or against the original in this case, because there is no print, okay? Once you have confirmation, then weld it out. So never weld anything out until you know dead sure you're correct, okay? People do this. They'll just start welding the whole thing out, and then somebody's like, hey, somebody's like, hey, did you get the correction on the print? It's like, oh, no. It's like, ah. So as a rule, never weld anything out flat out. So that comes through with anything you do here. You always want to tack it, check. Then once you have approval, then you go through the whole process. So be very careful about that. So we want to go with these things here. So we have some of Bruce is set up over there, so we already working on those. So we have here is we want to do set this, make some space on the table, set these up on there, and then we can bring a couple of MIG welders, ground them to the table, and then we have a couple pairs of you working on this thing and tacking them up. and then we'll get ready to call them in and take them, and then when they come back, then we can weld them out. So that'll be a lot of fun. Because the welding of this will be a lot of nice out of position. A lot of little crevices and stuff is very challenging, a lot of fun to do. So that's what I'd like to do today, and hopefully we can weld this out like as soon as possible, and that'll be very cool and a lot of fun. And when winter comes, we'll have our snowball working. So that's what I like to do. So we want to go to the table, make some space. Now, when you're working with more than one welder, and we have, like, say, you can have 2 or 3 welders hooked up to this table. I don't know if you went through this or not, but you must have 1 ground per machine, okay? So you can't have, say, like, why do we need multiple grounds if we're all grounded to the earth, right? Why do we need more than one? You know? Why do we need more than 1 ground? The machines actually sense the ground, their own ground. So the machine needs to, I know it's like, what the hell? They sense the ground to understand the conductivity of the arc. So if it only has 1 ground, they won't weld, they'll get confused. So they need to have their own ground. Even if you have like 10 people working on one construction, everybody must have their own ground hooked up. So it's a very important thing to remember. I've seen people get tripped up about this. Like, it's not welding. We have a ground, it's in the point of the earth. It needs to have its own ground. Now, the machines, they kind of diagnose the weld with the ground, so they need to see the whole current to weld properly. So that's very important. All right. Also part of it, here we're using templates, make sure everything's correct. It's a long process, but it's necessary when we do work like this. We don't have a print. We're working backwards. So we're creating a print where one doesn't exist. I did draw sketches for this. So this is kind of the fun part I always love through fabricating. Not having a print and working backwards, you know? Like CNC, they go forwards. They start with a print, they make something. Very often welding, fabricating, there is no print, and you're making the print the other way, but reverse engineering. It's a lot of fun. It's my favorite part of the whole welding fabricating process. It's a blast, especially when it's really complicated. It's like an adventure, it's really cool. All right, so let's go look over at the weld lab, make some space, and we'll move these over there and start tacking. So I'm going to stop this and upload it.